Thank you, Steve. So hello, welcome everybody. So today I want to talk about ingesting a sensor data for industrial use cases and how to build it in a reliable fashion, scalable fashion when you have a lot of data. So let me just quickly introduce myself. I'm Thomas Neubauer. I'm CTO and co-founder of Quix, and I have spent my whole life working with some shape or form of sensor data. Started with energy and gas prices for energy stock exchange, then working with the fleet data of different vehicles, then logistic of emergency vehicles, first responders, trying to synchronize ambulance with the helicopter and trying to save a person in the mountains, up to a motorsport. So in motorsport, we were, of course, getting data from F1 cars. We were trying to not just get this data of the ECU on the car to the database, but also to enable people to build decision insights on top of that, and to do it in a way that they can use their favorite tools like Python, Jupyter Notebooks, etc. And then after that, inside the McLaren group, we moved to projects where just using the know-how from racing, things like train projects where we were looking at the vibrations on a suspension to detect brake and suspension failures. So yeah, worked on lots of projects like this, and there are some things in common. There are good things to do and bad things. So I want to kind of go over them today with you. Hopefully you will find it useful. So first, the architecture. So what we quite often see, and to be honest, we even saw that in some places in motorsport, is that you have some sorts of data that could be a machine with OPC UA interface. There are others. Some machines have different interfaces. You can have MQTT style interface. But basically, you're getting some data from your machines, and then you would send them to a database. We see quite a lot of influx databases, to be honest. It's quite a popular database in the industry, and they have the whole stack with Telegraph. So a lot of customers originally send directly data from Telegraph to the database. But then, because obviously you want to do more with your data, maybe you want to change the shape of it, maybe you want to derive some metrics, or maybe just analyze them for alerts. Also, people doing downsampling, so they can look at a bigger amount of data for a longer period without choking the database. But the thing is, if you do it like on this slide, so you basically ingesting data to your database, but you also periodically querying it to make the batch job, what you're doing is you sort of using database as a message broker. It has to balance on one side an ingestion, and other side the query. Each database would be performed differently, whether it's influx, timescale, or QuestDB, they will have a different behavior. But basically, at some point, you gonna either have to sacrifice the query or ingestion. So either you're gonna start dropping the ingestions or queries, and it's gonna be kind of a balancing act here. And the whole problem comes from the fact that databases are not made for being a message brokers; they are databases. So the first thing you can do to improve this architecture is to put a message broker in the middle. So what we're doing here is that we're moving a database on the side. So now the purpose of the database is to persist data and occasionally serve a query when you need to look at a dashboard. Maybe you want to do some analysis in Jupyter Notebook. Maybe you want to build a report, but it's not constantly hammering the database with queries, which are periodically done on while you at the same time trying to persist that data. The second reason why this is better architecture is that everything you do, not just persisting, but also deriving new metrics, building alerting systems, downsampling data, changing the schema of your data, or mapping your sensor names to a company domain-specific names. All of that you do on top of message broker, like, for example, Kafka. And the advantage of that is that, well, first of all, it is a scalable solution. So it's actually made with the first objective in mind of a message broker is to be a distributed, fault-tolerant, scalable system. So it's made for scale. And so you can have a cluster with the different nodes that you will just be adding when you have more data. And secondly, there is a fault tolerance built in and retention of the data. So when you have some downtime or bug in your code, you are not losing data like you would if your database would be down in the previous architecture. So a lot of customers would obviously have their machines somewhere on the side. And we have a good connection situations where you can directly send the data to the topic. As you can see, we have customers that have the sites somewhere in a field, and that connection has to deal with a poor connection. And for that, you can, or you should, or I would rather say you must, you must switch from direct connection to Kafka to something that can deal with a poor connection. The same applies for number of producers. Kafka is not really made for being connected to thousands or millions of producers. So here we have a great example of a telegraph connected to a HTTP API gateway, which is the middleware between the topic. Now buffer here is to deal with the connection drops. So when there is no connection to the cloud, the telegraph will buffer the data. Other things we have saw, which works quite well, is the MQTT broker and topology like this. Now, these sources, whether it's OPC UA, whether that's the collector that's collecting, sorry, telegraph that's collecting it, or whether it's MQTT, it's always going to be slightly different data schema at the end, okay? And you might be tempted to use edge technology that you're using to transform this data. But this is another place where I would be advising not to do so, because if you do it wrong, or if you change your mind, or maybe you have not anticipated some change in your machines, well, if it was not working, you basically lost the data. You have no ability to restream, reprocess this data with a fixed version of your transformation. So definitely better to have the transformation here on the right. And if it's failing, you're going to just reprocess the topic which feeds that transformation. So keep the part on the left as lean as possible until it's reached to the safe boundary, which is the first topic. From that moment, you have the comfort of data being in a retention for time that you specify. It could be a week, month. Basically, it's about how much you are willing to pay for the safety for how long. So moving back to transformations, let's talk about these transformations because there's lots of stuff that makes sense in a industrial monitoring like this. So first thing is how the data coming in. So what you see on the left is very typical MQTT style structure, where the topic topology represents a sensor topology in the machine. So you would have maybe here a reactor A slash Arriva slash RTD slash temp humidity slash 1, 2, 3, 4, 5. And then in a payload, you would have a number of the temperature or humidity. Now, that might not be that practical in something like a metrics, derived metric calculation, as I want to show you in a second. But this also is a format that if you sync it to influx in my or other time series database, it might lead to either sparse tables or unnecessary queries in your Grafana's, for example, because you can't comfortably get a multiple sensors in one query in a format you want. So this is where you might, for example, do a transposition and have each sensor as a column, which would lead to what you see on the right, which is not ideal either, because you would basically get gaps like that, because these sensors might have a different logging frequency, or just they might be offsetted because they just don't share the same ECU. And therefore, the clock that is behind the moment when its temperature sensor is collected and sent is different. So with that, what you can do is to either do some interpolation, which might give you the comfort of cross-referencing of the parameters, but it might also lead to increase amount of data. So then it's more about what really is the frequency of data you need, and possibly what could be practical is, in that case, do something, for example, like this. So we know that we get change every 2 seconds, and despite having the data every second from different sensors, we kind of aggregate it to this because we're not getting more information anyway. So this is what you're looking right now. That is a dense table. This is what you're looking for. Something where the query is going to be fast, the persistence is going to be efficient. This is the format that time series database will be happy with. And also can the message protocol and even the time series database can do something like this. It can do deltas between the rows. What you also want to, or possibly might want to do in your pipeline, is to derive parameters which are not being sent from your sensors. In F1, this was actually a super crazy part because we have inferred from 300 raw sensor around 60,000 different columns. Some of them were inferred on the ECU, but some of them were inferred in the cloud. But it was really the huge ratio. But here you have example of wet bulb. So imagine you have humidity and temperature coming in, and you want to measure a wet bulb, which is more representative unit to how you feel the temperature. Now, as you can see here, this is why we need a table structure like this, or a data structure even before we send it to the database, because we want to maybe reference 2 sensors that might not even be coming from the one ECU in a machine. They might have slightly different timestamps. And here, because we already did the normalization, it's rather simple stateless operation to calculate the wet bulb here. So this is where we actually getting into getting the format of the data into a shape that people will be easily able to leverage in processing and post-processing as well. Good. So yeah, let's move to a back pressure, which is another great feature of this architecture. And it's sort of gonna explain why even transformations on top of a message broker like Kafka are resilient and reliable. But I think the influxing example here kind of explain the concept. So when you're ingesting data from your machine, what is happening is that data being produced to the topic in a Kafka broker, and they are being accumulated there. And at the same time, the influxing will be collecting this data from the topic and persisting them into the sink. But these processes are independent. So if the database cannot keep up with the amount of data that you're getting from your machines, you're not immediately losing the data. You're not immediately are in the trouble. The broker will act as a buffer here and allow you to solve the issue, either by giving more resources to your database or reducing the ingestion rate or possibly performing some sort of downsampling to keep under the threshold of what the database can ingest. So if we go a bit more into this view, what the green rectangles are here are basically the messages coming from machines. And here you see we have 6 messages collected. None of them have been saved yet to the database. And they will remain in this topic for a week, year. It's up to you how long you decide how to configure this topic. And the moment the first message arrives, what the influxing will do is it will start reading them one by one. So you see we start from offset 0 here, we're getting messages, and we're creating a buffer. Because saving each measurement to influx would be wasteful. You would waste a lot on HTTP orchestration, etc. We're creating batches of ideal size. And when we reach that batch size, we create one insert into database. And only when that batch insert is confirmed by the database, we create a checkpoint in the topic. So if we now would crash, or the hardware under the Kubernetes would have issues, we would just momentarily stop writing, get restarted to a healthy hardware, and continue persisting from this checkpoint. So we will never lose any data, even if we have a downtime in influx, or if we have a downtime in our data platform, or the cloud underpinning our data platform had a downtime. And also, if we, for example, have some issue with the schema, and for that reason, database can accept this data, again, we have time to do something with it and not lose any data. Yeah, so that's the most common stuff we have run into. Do you have any question? I will check if there's something in a chat. I don't see any questions. Well, if you have ones, I'm here to answer them.
Yeah, if you've got any questions, please use the Q&A section down at the bottom of your Zoom client there. I can ask you a question, Thomas, while we're waiting for people to type in theirs, if any come. So I've got a question about handling data quality issues. So would you handle those at the edge, or would you actually handle those in the cloud in a more centralized manner?
Yeah, let me go back here. Yeah, so this is a good point. I would definitely try to reduce the logic that I have outside of the safe perimeter of Kafka. So that will include the data quality checks. It will include any logic that would handle missing values, any filling defaults, all of that. Because if I do anything wrong in that logic, and I'm not in a Kafka perimeter, I might be overwriting data. I might be actually removing a useful piece of information which I can't reprocess later because this raw data are gone. So what we're trying to do is to keep the data as raw as possible and also touch the data as little as possible, because the bugs and problems coming from referencing columns that might not be they might cease to exist in the data. So limiting all of that to that blue boundary when we reach the first topic in a Kafka broker, because then we have ability to sync the data. So we quite often see that the raw database is actually not in flux, but something binary like iceberg or just a blob. So then can be replayed, or you can use the temporary persistence of the topic to reprocess the data. But yeah, not do it on the edge where you don't have the features of your broker.
So you touched on, just to kind of clarify that point slightly, you touched on kind of data reprocessing and handling sort of bugs or issues with the code. But I guess another reason to reprocess the data would be changing business requirements, right? So if the company decides they want to also capture some other parameter or also gain value, handle some other parameter in the data that they weren't handling before, they can actually create the code, create the transformation, the business logic to handle it, and then reprocess the data that they've got stored in that left-hand database, the one that's attached directly to the topic.
That's exactly the case. Quite often we will see reprocessing like that. We even working on a product feature around it, because it's so common across the customer base. So people can reprocess from the cold storage. And the beauty about most databases is that if you use them correctly, they will allow you to do the overrides. So for example, in Flux here, lets you to do a override as long as you keep the tag combination intact. So you don't have to even then manage the versions of the different data in your Influx and in your dashboards and in your systems. You just reprocess them, and they would appear the latest version.
Thanks. So we've got a question in the Q&A. Do you want to, can you see that, Thomas?
Yeah, just a second. Q&A, yeah. From Helen, you spoke earlier about replaying a topic in a simulation environment. Can you explain where that fits in? Yeah, so if you look at the diagram that we have now here, and we look at the database on the left, the one going directly from the raw topic, we will have a sink here, which is actually not for Influx, but would be for blob store. And we would save the data exactly how they were sent to topic. That includes things like timestamps and things like headers, etc. That will give us ability to later reprocess or restream this data exactly how they were collected. That means not just the data information, but also the velocity of data, the bursts of data, because what we have learned quite painfully is that when you're building batch systems or when you're building just request response systems, it's much easier to to unit test them for input and output. But systems like this will quite often fail just because how data being collected, time alignment, something being ahead, something being delayed because poor internet connectivity. Or sometimes some system in your machine will have downtime. It will create a buffer and then send a burst, and just your logic didn't expect that burst. So yeah, so we will have here the blob sync, and then the replay would come straight to that blue topic on the left. So you will just be replaying in your dev environment the experiment. And so you can then, without actually running your machine, which that might be expensive, whether that's a F1 car or OPC UA interface, you're just pressing a button and you're getting experiments based on a different situation that happened in the past.
Okay, thank you. It doesn't look like we've got any more questions, but obviously anyone can ask questions if you reach out on Slack or indeed once this goes onto YouTube, you can ask questions there as well. So yeah, if there's no more questions, we'll close it here. And thanks everyone for joining. Thanks, Thomas, for presenting as well. And yeah, we'll see you on the next one.
Bye-bye.
Thanks, everyone. Bye-bye.